Lab 1. Today I'll be showing you a video of a tennis ball going across the screen. It's shot by an air cannon. Then I'll show you the data and tracker and how I related that to my model, and the similarities and differences in the model in real life. Here is my video. As you can see, the tennis ball shoots across the screen and bounces off the wall. The video is slowed down to 1/4 of its speed so that you can see the tennis ball, and it is shot at 120 frames per second with an iPhone 5S. Here is a ruler that is 0.9 meters. Here's a calibration stick, 0.9 meters, and some other distances that will come in handy later. Our axis is set to the initial position of the ball, and our velocity is gathered from the last point before the ball hits the door. In Python, we set the range to 1.3 divided by 2. We get 1.3 from tracker, where we see that the video is 1.3 meters across. We divide it by 2 because the center of the screen will be 0, and the far right side of the screen will be half of 1.3. The far left side will be negative half of 1.3. Here are some other values: the radius of the ball, the size of the door. Here's the velocity of the ball. Here's acceleration of gravity. I had this in for extra dynamic. The initial position of the ball is 0.1 meters to the right of the screen. This is the elasticity coefficient. Basically, when the ball hits the wall, it will only retain 0.712% of its velocity. And the final time we also got from tracker. Delta T is 1 divided by 120 frames per second. This is the condition to allow the ball to bounce. When it hits the wall, it'll multiply by the elasticity coefficient. Here's the net force with gravity, just as an extra dynamic, not part of the observation. When I run this, it'll run at 1/4 of the speed, just as in the video. Here's a chart of the predicted versus observed times. As you can see, going toward the door in one direction, they are very similar. Once they hit the door, the tennis ball is compressed and slows down. However, in the model, it keeps going and then goes back in the negative direction. The assignment was for one direction, however, I wanted more of a challenge. Here is the graph for one direction. As you can see, they're very similar. There are 2 questions that I'm supposed to answer. What if, when you analyzed your video data in tracker, you made a choice of the orientation of axis? Discuss briefly how your results would change and how they would remain the same if you flip the axis. Here in tracker, you can see the axis at 0. If I flipped it, nothing would change. The ball would just be traveling in the negative direction. What does it mean? What do your observations mean? Can they be predicted well by your computational model? When you set the net force equal to 0 in your model, is it possible for you to say how many pushes and pulls are added together to give 0 net force in the case that you observed? No, it's not possible to know how many pushes and pulls there are, but 0 is close enough because of the great speed of the tennis ball and because we're only in the second week of physics. Thanks.